Uh, so we are back with bathroom stalls, and this time we are going for the more efficient approach. In case you haven't seen the previous video for this, which explains the problem and easy approach for this, you can check that out in the description below. Okay, so we talked about a segment that we have and us breaking it into two parts. So what are those two parts? This segment of size n can be broken into sizes n by 2 and n minus 1 by 2. What about these two segments? This can be broken into n by 4 and n minus 1 by 4. This one can be broken into n minus 1 by 4 and n minus 1 by 2 minus 1 by 2. So these are the kind of values that you'll have, and these segments can further be broken down into smaller pieces. Now I won't go into the proof of this, but the maximum difference between the rightmost term and the leftmost term for any given level of the tree. So when I mean level, this is one level of the tree and this is the other level of the tree. So for any given level of the tree, the leftmost term and the rightmost term, which means the largest term and the smallest term, have a difference of at most 1. Okay, and if you are a mathematician, then you'll probably be able to find out that this thing is a non-homogeneous linear recurrence, and after solving it, after reading this silly paper, there's something called a of n plus, we won't get into that, but basically this term up to any level can be defined by, let me cheat a little here, so it's n plus 1 by 2 raised to the power n minus 1. So this, let's call it something else, let's call it d. So the depth at which you're going, 2 raised to the power that, and in the numerator you have the size here n plus 1 and this term minus 1 as your rightmost term, which is your smallest term, and your leftmost term very obviously is n upon 2 raised to the power d. So if you have a look at these two terms, they have a maximum difference of 1. This is smaller, this is larger, maximum difference of 1. What does that tell you? If they have a maximum difference of 1, the number of segments having distinct lengths is at most 2, which in turn tells you that if you just store the number of segments that you have for a particular length, you can store it very efficiently. Alright? So let's do that. Let's have this small array which is going to be storing segments of different sizes. And as an example, let's take n equal to 100. Or let's make life easy and let's choose 8. Smart boy. So this is 7 now. 7 by 2 becomes 3. 8 by 2 becomes, what does it become? Becomes 4. What about this? 8 by 4 becomes 2. This in turn becomes 1. This also becomes 1. 8 minus 1 by 2 4 minus 1 is 3. 3 by 2 becomes 1. And this becomes 1 and 0. What about this term? Again, it's a mirror image of this. So this is 1. What about this term? 8 minus 1 by 2. Anyway, we have this term, So 3 minus 1, 2 by 2, which is 1. So good. Seems like the math that I did earlier was not very wrong, at least. And you see that the leftmost term and the rightmost term have a difference of at most 1. Right? You can try it out for larger terms. In case you find some discrepancy, in case you find something wrong, please point it out, because I'm not 100% sure that I got this mathematical formula right. But if you think of it logically, it should work. Now, for any given value k, or here, how does the segment behave? So the original segment is of size 8. When you put one person in, it breaks into two parts, which is over here. So you go down one level. So once you take one person in, it goes down one level. To go down another level, you need to bring two people in to break these two parts. So for the next level down, you need two people. What about for the next level over here? So we went to level 1 with one person. We went to level 2 with two people. To go to level 3, we need 1, 2, 3 and 4 people. So for the next level, we need 4 people. And hypothetically, if you need to go down this level, which in fact you can, so you can go to 0, 0 also. You can basically use up this segment also. So 0, 0, 0, 0 and so on and so forth. To go down to the 4th level, we need 1, 2, 3, 4, 5. 5 people. Do you see a pattern over here? Well, if you had people here also, if you had 1, 2 and 3 more people, then this would have been 5 plus 3, which is 8, which is the double of 4. 4 in turn being the double of 2 and 2 in turn being the double of 1. So what is basically happening is we are taking people, and to go down one level, we need 2 times the amount that we needed to go down the previous level. That in turn means that k can be expressed as a number, which is k equal to 1 plus 2 plus 4 plus so on and so forth up to 2 raised to the power x plus some quantity y, which is k equal to 2 raised to the power x plus 1 minus 1 plus some quantity y. And here you're trying to take x as large as possible. So we'll keep that in mind, but let's come back to the tree now. The number of distinct values you have per level is 2. And you can say the count of the number of segments of that value by looking at the parent. So let's say that we have 500 segments of size 4. When you go to the next level, those 500 segments of size 4 will be broken into two parts. 500 segments of size 2 and 500 segments of size 1. Similarly, if you have 600 segments of size 3, then now in the next level, after the next level has completed, you'll have 600 segments of size 1 and 600 segments of size 1. So that is in total 600 plus 600 plus 500, which is 1700 segments of size 1 in this level and 500 segments of size 2 here. So let's just do that. At level 1, we have two types of segments, size 4 and size 3. The count of them is 500 and 600. On level 2, we have two different types of segments, 2 and 1. Count of this is 500 and count of this is 500 plus 600, because it came from the parent. This one broke into two different parts, plus 600. That's because these two are equal. So 500 plus, that gives you 1700. And you see now that we have a method by which if we go down level by level, we can tell the number of segments of what size will be there in that level. And how fast are we going? Well, every time you go down one level, you're getting rid of 2 raised to the power x from k. So I'll just get rid of this equation over here. Every time you go down to a depth d, you get rid of 2 raised to the power d from k. So how soon will you be rid of k entirely? K minus 2 raised to the power d should be equal to around 0. So that will be k equal to 2 raised to the power t, and that gives you log to the base 2k will be d. So this is your asymptotic complexity now, and that's very fast. So in just these many operations, log of k operations, you'll be done. But here, of course, we are assuming that k is a perfect power of 2. So what happens if k is not a perfect power of 2? What happens if k is 6? So that gives us k is equal to, the first person breaks it into 2 segments, so that is 1, plus second 2 people break it, get us to the next level, so that is 2, plus then we need 4 people to go to the next level, 4, plus, do we have enough people? Do we have 8 more people? No. So this sums up to 7, this is 1. So the way that we can find out the frequency of the segments after these many people have entered is this way, is by just taking the parent and then finding the frequencies of the corresponding child blocks and then adding them up, summing them up. So over here you're seeing that we are going down 3 levels. We are coming over here 1, 2, and on the third level we break this into 2 parts. So that's the first break on the third level. So this is the point that we are at. Breaking into parts 0 and 0. So that's what we need. And going down the levels is easy, because every time you're going down the level from the parent to the child, you just note down how the parent breaks into parts, and their corresponding frequencies are then added to the children frequencies. That's all. You just need a array of size 2 to actually do this. So you'll create a new array and then you'll set the values and the frequencies, corresponding frequencies. But once you're done with this, once you've gone down as many levels as you can, which is here, you need to traverse over here. So that is a little tricky. You need to basically go down to the proper level and then find that segment which you need to break. So that is an offset which is given by this extra number, which is not a power of 2. And to answer for this part of the problem, we need to do something like binary search. So initially you have a segment of size 8 and it breaks into segments of size 4 and 3. But that's not enough information for us. In fact, it breaks into one segment of size 4 and one segment of size 3. So that isn't enough information for us to make our decision. And so when you're at the root, you need to make a decision. You need to say whether I need to go to the left subtree or to the right subtree based on your excess value. So if excess value is 1, with our current information, we cannot say whether we need to go to the left or to the right. So we need another method to find out the size of each subtree. And the size of this subtree is given by the number of segments that you can have on the very last level that you can go to. So what is the very last level that you can go to in this example? 3. 1 plus 2 plus 3. So these are levels. So that is 3, which is over here. On the last level, the size of the subtree rooted at 4 is 4. And the size of the subtree rooted at 3 is also 4. No, in fact, I'm sorry. The size of the subtree rooted at 4 is 3. These are non-zero segments. And the size of the subtree rooted at 3 is 2. Okay. So what we are going to do is we are going to go to the root. We are going to call a function which is going to find out the size of this subtree and going to find out the size of this subtree. How is it going to do that? Well, it will take this value 4 and perform these operations. It will go down the tree as much as it can up to the last level that you can go to, and then find the frequencies of all non-zero segments. So over here the frequencies of those segments are 1 occurs 3 times. Just rub this out. One occurs 3 times. And 0 occurs once. So what is the size of the subtree? Size of left subtree is equal to 3. Similarly, what is the size of the right subtree? You go to the last level that you can go to, and over there your frequency array will have the counts of 1 occurring twice and 0 occurring twice. So that will be size of the right subtree will be 2 plus, this won't be counted, so that will be 2. Alright, now you have the sizes of the left subtree and the right subtree. You have this excess value with you. Is 1 greater than or equal to the size of the left subtree? No. So then you will go to the left subtree, which is over here, 4. That's how you make your decision. If this value was equal to 6, then you would be going to the right subtree. And so in a way you are doing binary search. You are getting rid of half the nodes at any given point of time. So continuing with that example, we come to 4. And now 4 has 2 children whose subtree sizes need to be found out. So again you call the same functions. You go down this level. You again come to the conclusion that 1 occurs twice for the subtree rooted at 2. So that is 1 occurs twice and 0 occurs 0 times. Which means your new left subtree is equal to 2. Your new right subtree, which is rooted at 1, has 1 and 0. So your new right subtree has just one element. And the excess value is still 1. So that tells you that you need to go to the left subtree, which is over here. Finally, your 2 children are 1 and 1. They are at the last level. So all you need to do is find out if xs is 1 or xs is 2. If xs is 1, then you need to go to the left subtree. And if xs is 2, then you need to go to the right subtree. And that is your base condition. Once you have found the subtree that you're looking for, which is this one, then you'll be breaking it into 2 parts and then printing out what you needed, which is min of the person on the left and the person on the right, which is 0 and 0, and the max of these 2 terms. This is a 0 and this also gives us 0. So finally, when you are going to be breaking this segment, you will have max and min of the people next to you, of course, equal to 0. Alright, so we have solved this problem. So what is the time complexity of this? Firstly, you're going for 1 plus 2 plus 4 plus so on and so forth till 2 raised to the power x. And you do not have 2 raised to the power x plus 1. You can't, because otherwise you would have added that to the levels. So you do this, and each operation when you're subtracting from k is order 1. So that in turn tells you that 2 raised to the power x is x plus 1 is greater than or equal to n, which in turn tells you that log of n base 2 is equal to x plus 1. Now x is equal to this value. So order 1 for each, so order log of n is the complexity for this operation, for finding out the number of levels that you need to go down. On each node, we were finding out the sizes of the left subtree and the right subtree. The left and right subtrees go down in a very narrow fashion with at most 2 distinct values per level, and then give you the count back. So what is the cost of that? You go down log n levels, that is the height of the tree, and each operation takes order 1. So log n for every node that you need to go to. The number of nodes that you will be going down is again equal to the height of the tree itself. So this gives you log n, this complexity, into log n, which is the number of nodes that you'll be touching, into order 1. So that's okay. So your final complexity is this, which is order log n the whole square. Alright, so not too bad. A very big improvement from n log n, of course. And now you can answer queries for size 10 raised to the power 18, which is what the large data set was giving n as.
So that's it for bathroom stalls. In case you have any doubts or comments, please leave them below. I'll be sharing the code and relevant links in the description. And if you want any notifications for future videos, you can subscribe. So until next time, see you.